when this idea was put forward, it was intended to be a lecture on telling archaeologists principally how different rocks that they come across can be identified, but without damaging the rocks. So no acid, no scratching of them. And you know, it's hard enough to recognize rocks for geologists anyway, without even restrictions like that. So I thought about it and came up with the idea that it would be more useful just to refer to the features that can easily be seen and make the main purpose an account of how the rocks themselves were formed. Now, there's a course book that goes with this, 6 Common Kinds of Rock from Ireland, and I wrote this about 2008, and it was 2 copies of it were sent to every school in Ireland, along with a bag of rocks. And I think 60,000 bits of rock altogether went out. And there was a lot of help from my family and friends and students to put it all together. It was a huge effort. So primary schools, secondary schools, north and south, all got this book and a bag of rocks. And if it's available online, but if you don't find it easy to get, there's my email address, isanders@tcd, and I'll just email you a PDF if you want to get hold of it. Much of the material in the course then will come from this little booklet. And the 6 rocks themselves are these: sandstone, mudstone, limestone, basalt, granite, and schist. Okay, so a little bit about the motivation for this enterprise with school teachers. It comes from a famous Irish myth. It's called the Sugarloaf Mountain, which is claimed by many teachers to be a volcano. And I was a little bit alarmed at this myth, this mistruth, and decided that the only way to put it straight, the Sugarloaf, of course, is not a volcano, in case anyone believed. It's actually made of hard sandstone. And the rocks beside the hard sandstone are softer, and they've been eroded away preferentially over time, leaving the peak standing there. So that's the real story of the Sugarloaf. So to help to set the record straight, I started this rock set to infiltrate the educational system and get in on the bottom row. And it's not been entirely successful, because even last year when I was teaching a freshman class in Trinity, a show of hands still showed that some of them arriving here thought it was a volcano. Well, enough of that. Let's get on with the lecture. The first lecture, I'm calling it Geology Meets Archaeology. And here's the questions that I'm going to address. What happened 11,700 years ago? What was made from stone and when in the Irish archaeological record? The 6 common kinds of rock, what do they look like and how were they made? Then what are the 11 geological periods? And what does a geological map show? So here's the first question. What happened 11,700 years ago? And the clue to 11,700 years ago is an important time because it marks the start of what is called the Holocene epoch. And most of archaeology fits into that time. But what's interesting about this period is that 11,700 years ago, Ireland wasn't like it is today. It was actually covered in ice. This picture shows a house and soil, and underneath it, if you were to dig a hole, you would find soft, stony sand and clay. And underneath that, you come to hard bedrock. And this arrangement can be seen, for example, here in a cliff in Sutton. You can see the hard bedrock below and this soft material above. And that soft, sandy, stony material is called boulder clay. And boulder clay holds a clue to what went on 11,700 years ago. And at that time, Ireland was covered in ice, an ice sheet hundreds, perhaps up to 1,000 meters thick. And year on year, the snow landed and it didn't melt away. So the sheet got thicker and thicker and it got heavy and it flowed under its own weight, generally outwards, down from mountains and out southwards generally. And as it moved over the land, any solid bits of rock in its way were plucked and ground along. And so the bottom of the ice, the moving ice, got extremely dirty. And then at 11,700 years ago, something remarkably happened. The temperature suddenly warmed up, really quite dramatically, and the ice began to melt. And when it melted, all that muck that was in the bottom of the ice was left draped over the country as this sheet of rock, which we call boulder clay. Here is another picture of that boulder clay, which has just been washed away by a winter storm on the coast. And you can see the scratch marks and the gouge marks left behind by chunks of rock that were embedded in the bottom of the ice, the moving ice sheet, that scratch these lines. They're called striations. Okay, so the next question is, how do we know that it was 11,700 years ago that this happened? And now we have to move to another country, to Greenland, to get some answers. And it comes from deep cores that were drilled into the ice, and these cores were recovered. And here's a section of one of those cores, 19 centimeters long, from an enormous depth, nearly 2 kilometers down. And you can see light and dark layers, and they are annual dark light pairs that are visible. So starting from the surface, we can count down these cores to see which year you're in, how many years ago you were when that particular snow fell. Now, what's more important is the ice carries in it a record of the temperature. There are two kinds of oxygen in the ice, two kinds of oxygen in the H2O, O18 and O16. And the ratio of those two in the ice depends on temperature. The lower the temperature, the lower the ratio. And so temperature has been inferred from that ratio in the ice. And here is a record of that temperature going back for about 1,700 years. This is time along the bottom. There's the present, and here's 17,000 years ago, I should say, 17,000 years ago, going through to the present. And this is the inferred temperature from the ratio of the oxygen isotopes. Okay, so moving forward in time, you can see the temperature in a very jagged way, going up and down, getting really quite warm at this time, just under 15,000 years ago, and dropping down and being freezing again. And then this point here, a nearly vertical line, it changed within a matter of a decade or maybe 10 or 20 years or so. It's suddenly warmed up. And the period since then, as I said, is called the Holocene epoch, and that's where archaeology fits. You can see here as well that it didn't get right up. This is the current temperature over Greenland, about minus 30 degrees C on average, very cold. It didn't warm right up to current temperatures until about 10,000 years ago. And that's really when we see the first evidence of people here. So what was made from stone and when during that period when people arrived? Well, the first people were hunter-gatherers, and they moved up presumably from the south, and they lived here from 10,000 to about 6,000 years ago during a period that's called the Mesolithic. Here is something I picked up from Mr. Google. He was great for telling me stuff. I don't know if it's true or not, but here it is. Supposedly a 9,000-year-old polished stone axe from the Mesolithic people that lived here. Better known, I think, about the Mesolithic period are the flint implements, like arrowheads and blades, like these known as bandflakes, collected from Northern Ireland. But about 6,000 years ago, some new people arrived and displaced the Mesolithic hunter-gatherers. And these people were farmers. They were thought to come here from the Middle East, and they lived during what's known as the Neolithic period. That's from 6,000 to about 4,500 years ago. And they built Newgrange. And they left behind a wealth of artifacts and tombs that most people associate with Ireland's more distant past. Things like our local dolmen here in the Howth, and this famous dolmen in Paul na Brún in the Burren, and axe heads, polished axe heads galore. About 20,000 of them have been recovered. And other tools, like this beautiful saddle quern. found near Waterford. And this basin in Newgrange made from the rock granite, and it's about 1.5 meters across. It's huge, and it was chiseled out of stone. So the Neolithic period left behind a wealth of things for us to ponder. But the Neolithic ended, and people, the Neolithic farmers, were displaced, and possibly violently, by the next folk to come in during the Bronze Age, called the Yamnayans. And they, this skeleton of one of them was recovered on the road approaching Barry's pub on Rathlin Island, and they dug it up when they were developing the road. So here we are. Anyway, it's 4,000 years old, and its DNA has been sequenced, and it turns out to be very similar to that of modern Irish people, and quite different from the farmers that were there before. So this colleague of mine, Dan Bradley in Trinity, has done a huge amount of work on sourcing, sequencing this DNA, and he has demonstrated, or proposed anyway, something like this, that the first people, that's the lower red line, the farmers came from the Middle East via Anatolia and made it to Ireland. That was the Neolithic farmers. And then about 4,500, or a little bit younger than that, Dan suggests 4,000 years ago here, these people moved from this area called the Pontic Steppe and got as far as Ireland. They also moved east, and it's believed that these people were the source of the well-known Indo-European language group. They brought their language with them when they traveled. Well, next came the Iron Age. That lasted from about 2,500 to 1,500 years ago. And it coincides with the time that the Greco-Roman civilization was in operation. And it also is the time that the Celts were in Ireland. And the people living here, the Celts, during the Stone Age, during the Iron Age, they turned, some of them, to stone carving. There's a beautiful stone carved here called the Turo stone in County Galway, with a typical Celtic style of carving on it. From 1,500 years to 500 years ago, the next period is the medieval period. Ireland's past is, in those times, is recognized, is represented, I should say, by, for example, the beautiful high crosses of Ireland, like this wonderful carving, Muradach's cross from Monaster Boyce, which is 12,000 years ago, and belongs to the early medieval period. And later than that, wonderful stone carving in abbeys and monasteries during the late medieval period, like this carving in Holy Cross Abbey. So that's, if you like, a summary of the people that lived here and some of the things they made. I'll just quickly go through it again. Let's start from present day. The last 500 years, going back, we can call that the age of discovery. That's where we're living now and discovering all sorts of wonderful things. The Middle Ages, or medieval time, the 500 to 1,500 years ago. And then the Iron Age, or the Greco-Roman period, when the Celts were here. That's 1,000 years more before that, from 1,500 to 2,500 years ago. Then the Bronze Age was quite extended, about 2,000 years, from 2,500 to 4,500 years ago. Before that, then, the builders of Newgrange, the Neolithic farmers, 4,500 to 6,000 years ago. And then before that, the Mesolithic age in Ireland, 6,000 to 10,000 years ago. And then a period when the climate was settling down, getting decently warm, back to this amazing event of 11,700 years ago, when the temperature suddenly jumped up and the Holocene epoch began. Right, well, that's the kind of archaeological story for tonight. I'm going to switch now to geology. and ask the next of these 5 questions, the 6 common kinds of rock. What do they look like and how were they made? Okay, so here they are again: sandstone, mudstone, limestone, basalt, granite, and schist. Now, of those, the most distinctive, I think you'll admit, is granite. It's quite obviously speckledy, light-coloured and speckledy. And if we look at it more closely, you can see that it's made of different ingredients. And I try and see if I can pick some out for you. Quartz is one of them. The ingredients are what geologists call minerals. Quartz is one of those ingredients. It's clear and glassy, and it actually looks rather grey. There's some quartz just there where I'm pointing to. It looks rather greyish in this photograph. It's glassy, in fact. And then most of the rock is this mineral, feldspar. It's white in the photograph. And then muscovite mica forms very conspicuous shiny plates. And if you've got a knife blade to them, you can prise them apart to make thin flakes of this mica look like fish scales. And finally, biotite mica is black and forms just a small number of the grains in the rock. Now, minerals are chemical compounds. The chemical composition of quartz is written SiO2. That may seem a bit far away from anyone who's not done chemistry, but it's not so difficult. Everyone's heard of CO2. Well, take the C out and put the Si in, and you've got silicon dioxide, which is what quartz is. Now, I'm going to try and show you some of the other rocks in the flesh, so to speak. So here is the granite.
Yeah.
And maybe if I turn it in the light, you might be able to see the different minerals, and the muscovite mica might be glinting for you. Okay. And then another one that's conspicuous is this one, schist. And as I turn it, can you see it glistens? It's a very distinctive kind of rock. So that's the schist. And when it comes to the others, they're different colors, but they're all rather uniform and averagely fine-grained. So how do we tell them? This is the sandstone. And what a geologist would do is to test its hardness. So here we are. And if I try and scratch it with this penknife blade, it makes no impression. In fact, if I reverse the process and scratch the penknife blade with the sandstone, it'll scratch my little knife. So sandstone is very hard. That's a useful one. And secondly, if I, got here my hand lens, if I look at it with this lens, I can actually see the little sand grains in it. So that's a way that you can actually check sandstone very often in the field. Okay. When it comes to mudstone, that is really soft. And if I can show you, there we are. And if I drag the penknife blade across it, does it make a line? You can see the line? I don't know. It's left a gouge. It's extremely soft. And it tends to break into flattish pieces. Look at the shape of this, rather than angular lumps and blocks. That's the way mudstone tends to behave. Then limestone. That's also soft and scratchable. But there's something else about limestone that geologists enjoy. And that is if you put a little drop of hydrochloric acid on it. Now, I hope you can see this. And this is hydrochloric acid. And I have to be careful it doesn't go into between the keys of my laptop, or I'll have problems. Now, can you see that? Can you see it bubbling?
Yeah, very good.
Okay,
Yeah.
so that's a very good test for limestone. It fizzes with hydrochloric acid. And I'm told that archaeologists wouldn't want to destroy their wonderful, valuable possessions by putting acid on and spoiling it. But if you've got a broken end, who's going to know? And you can just do a check like that. Okay, and then what's left? Basalt. That basalt is also rather uniform and it's very dark in color, and it can be scratched, but with difficulty. It's quite hard. Okay, so there we are. Those are the 6 rocks and what they look like. Let's go on to ask what they how they were made. And here's a summary of what we just did. There's a sandstone. It's hard. You can't scratch it. Sand grains are visible with a lens. The mudstone was soft and it broke into a platy shape rather than a block. The limestone, that's quite soft and it fizzes with hydrochloric acid. There's, if you like chemistry, CaCO3, 2 HCl's makes CaCl2 and H2O and CO2. That's only for those of you who like chemistry. If you don't like chemistry, you don't even need to know that at all. Basalt, that's quite hard. And I didn't mention it at the time, but if you look through a hand lens, you can see tiny elongate grains in it. They're not rounded sand grains, but little elongate, randomly orientated grains in basalt. There's the granite we looked at the beginning. That's very distinctive. And finally, the schist. It glistens and it splits into wavy bits. Right. So let's ask then the next question of how these different kinds of rocks were made. And we're going to start with sandstone here. And here's the process. You need a land surface where you've got high ground and a low area nearby. And these are the 4 steps that are involved in making sandstone. The first is that the existing rock up in the mountains here, it gets weathered and eroded and it crumbles. And the bits of that rock get washed into rivers and transported down until they reach a lower region. Shown here is the seabed. Okay. The grains are deposited on the seabed, and then with more and more time and more layers building up, the sand gets deeply buried and it turns into hard sandstone by a process called lithification of the sand grains. Now, that lithification is helped because the temperature going below the surface increases. In Ireland, it increases by about 20 degrees in every kilometre. So here's the surface, and this is going down, and there's the temperature going across. So it starts off at around 10 degrees, just below the surface. And so that means that 1 kilometre down, it would be 30 degrees, 2 kilometres, 50 degrees, 3 kilometres down, 70 degrees, and so on. So it gets quite a bit hotter. So the water in between those sand grains would be hot water by the time they're buried. And that would tend to dissolve a bit of the quartz and reprecipitate it and bond the grains together to make hard rock. That's lithification. It's a bit like what happens if you have a bag of granulated sugar and it gets damp and the moisture dissolves a bit of the sugar. And then when it dries out again, all the sugar grains are bonded together into sugar rock. But we see sandstone at the surface today. So there's a 5th step, and that is uplift and erosion. The deeply buried layers have to come up again. And here they are, still horizontal at Loop Head, these layers of sandstone, County Clare. Mudstone next, that has the same sequence of events, erosion and transport, deposition and burial, but this time of mud particles, tiny mud flakes. And they get lithified into mudstone. But limestone is a little bit different. In limestone, we're dealing with the accumulation on the seabed, not of sand or mud that's washed in, but of organisms, the shells of organisms that were living in the sea. And when they die, they fall to the bottom of the sea. And if there's an area of the sea where there's no sand or mud being washed in, that's all you get, just shells. And you get big shells and small ones. This is a limestone with some big fossil corals at Streeter in County Sligo. It's an accumulation then on the seabed of fossil shells, and these shells are made from calcium carbonate. So limestone ends up being made of calcium carbonate. The fossils in limestone are wonderful. Here's a whole suite of them. This is a beautiful picture, and it was published more than 100 years ago, so I can use it with impunity. I hate to think of some of the other images. I'm sure someone's going to kind of blame me for stealing copyright. Anyway, these are fossils in limestone from Ireland. Okay, now here we are, another picture of uplift and erosion. And this shows horizontal layers of all three, sandstone, mudstone and limestone in this sea stack off the North Mayo coast called Dunbristey. Okay, so I think everyone now I hope's got the idea of how these rocks are made. The three of them have got a common name. They're all called sedimentary rocks because they're formed by sediment accumulating and being turned into rock. Now, just in case you don't like this idea of huge amounts of uplift of the land and subsidence of the land, here's a little aside. This is Everest Base Camp. And found here are fossil ammonites. Here's one, ammonites in mudstone. And these are at nearly 6 kilometers up. And they started off as animals living in the sea, little animals like this, a kind of a squid living in the front end of a coiled shell. So these were in the sea and now they're 6 kilometers up. So if you ever don't want to doubt, don't. Land moves up and down. Okay, let's move on then to the next of these rocks. That's the first three done. Basalt comes next. And here we can see basalt in the making. This is in Hawaii. And hot liquid comes out of the ground and cools down and hardens and becomes black basalt. Okay, now that hot liquid, over 1,000 degrees centigrade, that hot liquid, geologists call that magma. Now, magma is called lava when it flows out on the surface. It's the same stuff, but it changes its name once it comes out. So lava and magma are the same stuff. This is basaltic magma and lava. And clearly this formed in a very different way from the sedimentary rocks. And rocks like basalt that are formed by the cooling down of magma are called igneous rocks, from the Latin word ignis, meaning fire. Okay, now basalt poured out over the Irish land surface, but 60 million years ago. And in one part, the lava formed a kind of a lake, which cooled and hardened. And as the rock solidified and shrank, it broke into these remarkable columns that everyone knows about. Now, the top part of the frozen lake has been eroded away. So what we're looking at here is a kind of a cross section through that lake, a nearly horizontal cross section through that original basalt lava lake. Okay, let's move on to granite. And granite is also an igneous rock. It's formed from magma, but this time the magma doesn't get to the surface. In this block diagram on the left here, you can see the granite in red, and it comes up from depth, and at some point it stops and inflates a huge underground like blister, maybe 10 kilometers wide. And there under the ground, it slowly cools and hardens. Granite is described as an intrusive igneous rock. And this red blob is called a granite intrusion. Okay. Now, of course, we see granite at the surface in Ireland. So to get to that stage, the diagram on the left has to have the rocks stripped off by erosion, and that exposes the granite at the surface today. And that's what has happened. So that leaves us with the last rock here, bottom left, the glisteny schist. How does that form? Well, going back to this picture of the granite, you can see the little dashed zone around the granite. That's where the rock got hot, very hot, and changed. It changed in appearance. That was originally mudstone, and the mudstone has changed into schist. And schist is an example of a metamorphic rock. The word metamorphic means change. That's meta, change, and morphic is form. So it's a rock that's changed its form. It was mudstone and now it's schist. So rocks can be grouped then into these three categories: sedimentary, igneous, and metamorphic rocks, like this. There we are. Sedimentary rocks are the top three, then the two, both basalt and granite, are igneous rocks, and the one on the left is a metamorphic rock. And the next three lectures, I'm going to take these in turn: sedimentary, igneous, and metamorphic rocks, and describe them a little bit more detail, more examples of the archaeological artifacts that we see made from these rocks. So let's move on and ask the next question. What are the 11 geological periods? Well, geologists like archaeologists divide time into intervals, and the main intervals that geologists use are called periods of time. There we are. There's 11 of them, and we usually name them counting from the bottom up. So we start at the bottom and go younger. So we say them in this order: Cambrian, Ordovician, Silurian, Devonian, Carboniferous and Permian, Triassic, Jurassic and Cretaceous, then Tertiary and Quaternary. Those are the 11 periods. And I put three numbers here. I think three is more than enough to try and remember, but the Cambrian period started 541 million years ago, and the Triassic period 252 million years ago, and the Tertiary period 66 million years ago. So what I'm going to hope you will be able to do is to remember these names in order and these three numbers, because that gives you a really handy frame of reference. If any of these names is mentioned, you can immediately put it into the context of when and what was younger and what was older than it. Okay, so to help you, this is something I learned from a school teacher years ago, and I've told lots and lots of people since. You can remember it like this. This is the mnemonic, and you read it from the bottom up, just as I did before. Camels often sit down carefully, perhaps their joints creak. And then for the tertiary and quaternary, I say thank you. Not very elegant at the end, but thank you. So those are the 11 periods. And just to help, there's three of them beginning with C, but that can be a bit confusing. So the guy who devised this mnemonic was very careful to choose names where the first three letters, there we are, the first three letters, Cambrian, Carboniferous, Cretaceous, the first three letters in the name of the mnemonic are the first three letters in the name of the period. Okay, well, I haven't quite finished, because those geological periods are grouped. They're grouped into three eras called the Paleozoic era, which goes from Cambrian to Permian, and that is actually normally split, and people talk about Lower Paleozoic and Upper Paleozoic. First three are Lower Paleozoic, the next three are Upper Paleozoic. Then these three, the Triassic, Jurassic, and Cretaceous, they are grouped together to make the Mesozoic era. And finally, the last two are the Cainozoic era. Well, I should mention that these names go back way before we knew anything about how old the rocks were. And they were based on the fact that all these periods, during all these periods, life was abundant on Earth and was left as fossils in the rock. And the kinds of living organisms gradually changed through time. So the fossils they left behind are different in the Cambrian and the Ordovician and the Silurian. So it's possible to see in layered rocks, with the oldest at the bottom and the youngest at the top, how life has evolved and the relative age going from oldest to youngest. So these names of periods are actually based on where we are in the gradual changing of life on the planet. I have one last thing to say, and that is what happened before the Cambrian. Well, I'm just going to say this. We call it Precambrian. Everything before the Cambrian, we just call Precambrian. And that goes back to this lovely number, a fourth number to remember, but you shouldn't forget that one. It's easy to remember. 4, 5, 6, 7 million years. that is when, I was going to say, that's when the Earth formed. Well, it's actually strictly when the solar system formed, because it turns out from meteorite studies that the Earth actually probably took about 30 million years to form. So it didn't form instantly. But 4, 5, 6, 7 million years then is the beginning of our solar system. Right. Next, what does a geological map show? Here's a geological map of Ireland. And the natural expectation is that these different colors represent different kinds of rock. In most cases, that's absolutely not true. Some cases it is, but for most of those colors, it's not rock. It's not rock type. It's the age at which the rocks were made, and particularly the sedimentary rocks. And so, for example, you can see across the country from east to west, the dominant color right across is blue. And those are rocks that were deposited. They include limestone and sandstone and mudstone during the Carboniferous period. Down here in the south, this brown color are Devonian rocks, rocks laid down in the Devonian period. They're mostly sandstones and mudstones. And these purple colors are lower Paleozoic rocks. Pale is Silurian, dark is Ordovician, and actually, to fill in the last one, this pale grey here on this map is Cambrian. The Cambrian, Ordovician, and Silurian periods, that's the lower Paleozoic, are shown here. And they are, in Ireland, mostly sandstones and mudstones again. This pale pink colour up here, that's basaltic lava. You see, it's tertiary. The tertiary began 66 million years ago. And as I told you, the basalt lava at Antrim, the Giant's Causeway, came out 60 million years ago, during the early part of the tertiary period. Okay, then. So I'd just like to mention these bits of purple that are surrounded like a sea of blue, they're like islands. These are lower Paleozoic rocks, that purpley colour, surrounded by younger Carboniferous rocks. And what's happened here is that the layers have been deformed a little bit. They've been bulged upwards a little bit in these areas. And the Carboniferous, the younger Carboniferous rocks, which were presumably once on top, have been completely stripped away. And the lower rocks underneath are showing through with these lower Paleozoic colours. And as a little exercise, I have produced on the back of that little booklet a line drawing map, a simplified line drawing map of Ireland, which you can see here. And you can colour it in. The divisions are the Precambrian, which is mainly out here in the west and northwest. Lower Paleozoic is lettered B, Upper Paleozoic lettered C, and the younger Mesozoic and Tertiary rocks letter D. So you can colour it in, and these are a kind of conventional colours: orange, purple, pale blue, and green, if you like. And then this rock, granite, let's go back. Sorry. Here it is, granite, is shown in red, irrespective of age. So rocks, the colours correspond to the age, but not for intrusive rocks like granite, which are shown typically by bright red. Okay, so I think that covers everything I wanted to say. So I'll say thank you for your attention. You've been a very quiet and attentive audience. Now, I have, do I dare, as a little 5 minutes, you know, my interest is in meteorites and things going like that. So will I just take the liberty of saying what happened before the Earth was formed? And here we think of time through distance and the speed of light. This little object here is an object in the solar system. It's 6 light hours away. It's called Arakoth, which means sky in Native American in a Native American language. And it was imaged by NASA in January 2019. And it took 14 years to get there, and it takes 6 hours for radio signal or light to travel the distance from Arrokoth. So our solar system is truly enormous. But if you think that's big, the nearest star to the solar system is this, Proxima Centauri. And that takes 4.2 years for light to travel. And our solar system, our sun and Proxima Centauri are just two of the stars out of a huge number in our galaxy. The number is, think of a number that's big, 100, no, that's not big enough. 1,000, that's not big enough. 1,000,000, that's not big enough. If you put all three together, 100,000 million, that's the number of stars that are estimated to be in our galaxy. And if you were to look at our galaxy from a long way away, it would look rather like this, like a huge fried egg. It's called a spiral-armed galaxy. And most of the stars are clustered near the middle, in the yolk. And we would be out here about 3/5 of the way out from the center to the edge. So we can imagine our solar system being located about here. Now, when astronomers look through telescopes at the stars in the center of the galaxy, they're looking at them 30,000 years ago, well before the start of the Holocene epoch. It was just yesterday at 10,000 years ago. 30,000 years for light to travel from the center of the galaxy out to us. Okay, so we're looking way back in time and the universe is huge. But if you think that's big, the next one is even more. That's this, it's called the Hubble Deep Field. What scientists did is to train the telescope, train the Hubble at a tiny gap between the stars in our own galaxy. The gap was so small, it would be the equivalent of a sand grain held at arm's length, peeking through between our own stars beyond. And each of these specks of light is a distant galaxy. And the number of galaxies out there beyond our own is estimated as about the same as the number of stars in our own galaxy, 100,000 million. And some of these galaxies are so far away that the light, we're seeing them as they were even before the solar system was formed. They're more than 4,500 million years old. In fact, some of them go back more than 10,000 million years ago, back to what's the beginning of the universe at 13.7 billion years, called the Big Bang. One final question. Here's a piece of coal, and atoms are very, very small. And this piece of coal, or carbon, has 1,000,000,000,000,000,000 atoms of carbon in it, one with 24 zeros after it there. Okay, there's the question at the bottom. Is this number of atoms in this small piece of coal more or less than the number of stars in the entire universe, the number of stars in all the galaxies in the universe? And the answer is, it's a lot more. There are many more atoms in that piece of coal than there are stars in the entire universe, assuming that our galaxy is an average one. And that's because 100,000 million is a 1 with 11 zeros after it. And if you have 100,000 million of those, you end up with a 1 with 22 zeros after it. This 100,000 million is a 1 with 24 zeros after it, 100 times bigger than the total number of stars in the galaxy. So with that, I really will say thank you very much, and sorry for squeezing that extra little bit in.